All right, so welcome everyone. So today we'll have the pleasure of hearing from our very own Andy Mummery, who joined us from across the pond after over a decade in Oxford. Finally, a change of scene. He is well known for his disruptive research in electromagnetic transients and for plunging deep into the depths of thin accretion disk theory. Please, Andy, take it away.
Thanks, Alex. I did change sub-departments in my decades in Oxford. Okay, so I'm going to talk to you today about supermassive black hole demographics with tidal disruption events. So I'll start with a broad overview of TDEs, as I'm going to call them from now on, to save time on tidal disruption events. So how we get them, their scientific or astronomical potential, and some of the challenges we've had as a community in describing them. I'll talk about the main sort of thrust of a lot of years now of research that we've been doing, which is how to weigh supermassive black holes with optical light curves from TDEs. And then I'll talk about the future of TDE studies, which is basically demographics of black holes with LSST and why you're going to keep hearing about TDE so much over the next decade. So let's start with a galaxy. Many of you are familiar with one of these. Let's say we live here. All I want you to take from this picture of a galaxy is that the center of galaxies are significantly more dense in terms of their stellar population than Earth. So the point of that being, if we zoom in on the center of our own galaxy, it's incredibly dense. The S star cluster, which is roughly 40 stars within a light month at the center where the supermassive black hole is. And for the purpose of TDE science, all that really matters is that this means that the stars don't just sit on nice elliptical orbits like they would if it was just a binary. A star may want to go around the supermassive black hole in the center, but there are many other stars, so there will be some gravitational n-body interactions. So this is going to be the entire of the dynamics in this talk. Okay, n-body gravitational interactions mean that sometimes you kick a star, you change its momentum, you change its orbit, and at least in principle, I've just solved these equations, you can scatter a star arbitrarily close to the central supermassive black hole. So if you get sufficiently close to the black hole in the center of a galaxy, the tidal force to the black hole can overcome the self-gravity of the star, and then your star ceases to become a bound object, you rip it apart, and you initiate a transient accretion episode onto the black hole. Yes.
But why do you focus on the stars close to the center? I would think most of these things happen much further away.
Yeah. I just like to show the S star clusters. Okay, there's no, they're not the stars typically that get scattered down. It's the influence radius. So if there's a finite volume in phase space which you can scatter a star into where it will be ripped apart, which means that this does happen. Okay, it's relatively hard to do. The tidal radius is relatively small. The region of phase space is small but non-zero. And so, if you do your galactic dynamics carefully, you get, carefully to the order of magnitude at least, you get a rate in a given galaxy of one of these close encounters every 10,000 to 100,000 years. Or in the optical transient space, this is 1% of the supernova rate. So the key is, if you look at 100,000 galaxies for 1 year, you find one of these. So that's basically what optical transient surveys.
Distribution is based on how many stars around the black holes.
Tell you what, this is an empirically true fact. Let's go with that. Dynamicists can tell you better how this is calculated. This is also empirically true. So what happens when you throw a star in a black hole? So for a brief period of time, it's very messy. The tidal force does work. You disrupt the star, you stretch it out into a stream of stellar debris. It wraps around the black hole a few times. There are collisions between these streams due to relativistic precession effects. This dissipates energy, presumably produces a large amount of light. But ultimately, on long time scales, you have an angular momentum in the problem, which was the angular momentum the star came in on. It's quite easy to dissipate energy. It's much harder to dissipate angular momentum. So eventually you form some sort of circularized structure. Okay, there's a radial scale in the problem. Yes.
Well, I was just going to ask, is this simulation is planar?
No, this is a projection of it. I mean, this is really old. I quite like Clement's his original simulations, but there are much better simulations than this now. Okay, and this holds up in the world of much better simulations.
Well, what you've said holds up.
What I've said holds up. This exact simulation is a decade out of date now. The premise is true. You form some sort of accretion flow, and then on much longer timescales, years to decades, this is going to accrete onto the black hole and produce further emission. Okay, so these have great potential. The reason we have colloquium speakers to talk about these things is they're going to probe the black hole mass function. Okay, so these should go off randomly. Any black hole surrounded by a cluster of stars, in principle, gives you a T. So you have a probe of the quiescent black hole mass function. They're going to be a really good probe, or they should be a really good probe of intermediate mass black holes. The reason for that is in units of the Schwarzschild radius, the tidal radius is bigger for smaller mass black holes. In principle, you could try and understand the black hole spin distribution. I won't have any time to talk about that today, but in principle, it's possible. You could try and think about the populations of stars in galactic centers. It takes two to tidally disrupt. If you had a really good framework for understanding TDs, in principle, you could think about the stellar mass distribution of distant galactic centers. And, they're fantastic probes of fundamental physics. Okay, these is effectively as close to a natural Green's function of the accretion problem as we can get. Okay, I'm going to take a mass and I'm going to dump it around a black hole that has previously no disk there, it's a quiescent black hole, and I'm going to watch it accrete over human observable timescales. So on an observable plane, these are fantastic observational probes of fundamental questions in accretion theory. We can watch jets switch on in some of these events. There's all sorts of interesting things. You could even, if you wanted to be really crazy, ask what the tidal disruption events look like in different metrics, Einstein's gravity, all these sorts. Okay, so observationally, to leading order, a TD is an optical transient. So we have about 150 optically bright TDs that we know of today, but they are fundamentally, as objects, multi-wavelength transients. So there's about 80 of them which are X-ray bright, and about 20 of them that are radio bright. This, I wish to stress, reflects how easy it is to observe things, survey completeness, not intrinsic rates of multi-wavelength emission. In fact, if you correct for how easy it is to find these things, the rate of X-ray bright and optically bright TDs is roughly the same. It's just that it's very easy to look at the whole sky all the time with an optical survey. And typically, we then find them in X-rays by following up these optical events. And it's very, very expensive to get any radio observations. So this 20 radio bright TDs just reflects the expensiveness of those observations. Okay, and what do they look like when they go off? Okay, so you've ripped apart a star. Some emission results from this event. What do they look like when we get to Earth? So I'm going to tell the story of this through sort of the canonical TDE. It's called Assassin 14Li, discovered by Assassin in 2014. Okay. In the optical and UV, you get a very bright flare. So about 10 to the 43 up to 10 to the 45 erg per second. So brighter than supernova. They decline rapidly at early times. If you fit an exponential, say, to the population, you find e-folding timescales of sort of tens to hundreds of days. The spectra are very blue. You may be interested in. And then at late times, so after say 1 year, you see a flat line in the optical UV, and you may think this is the galaxy that it happened in, but this is not true, okay, because we're observing the whole sky all the time, so we know how bright the galaxy was before the TDE. This is galaxy subtracted data, so this is real, this plateau is real. So something happens at day 300, which takes you from a light curve with an e-folding time of maybe 10 days, to something that sticks around for 1,000 days. And actually 14Li went off in 2014. So you can extend this light curve out to 4,000 days now, and it's varied by a factor 2 in those 4,000 days.
And the rise here is,
this was just because it happened to be behind the sun when it went off. So the previous upper limit was minus 90. It just happened to be behind the sun. But there are TDEs with rises, the rise time tends to be a bit shorter than the decay time, or like never as short as days, but more tens than hundreds of days in the rise.
So wasn't there a canonical T to the minus 5/3?
Yeah.
That's just
So, yeah, it was a good effort by Martin Rees, but no, doesn't happen. If you fit power law decays to this flare, you get indices from -1 to -5. It's not shown up.
But not even close enough to the peak.
Well, if you include as little data as you want, you can always put 5/3 through it, but no, if
I don't
you.
mean faith, but also
Oh, I mean, they are well described by power laws, but the index is not 5/3. It's a wide range of decay.
This is the fallback rate directly.
This is not the fallback rate. The mass does fall back because T to the minus 5/3, you can simulate the hydro, but the light that comes out generally does not.
When it comes to weighing the black holes, is it the rise time that is more powerful in doing that? Or
Okay, so as our colloquial speaker the other week said, this we're not getting much out of scientifically. I'm going to argue that this is how you weigh the black hole. That's my favorite. Okay. X-rays, they're equally bright in X-rays. They can hit 10 to the 44 erg per second in soft X-rays. They decay rapidly. They do not plateau in the X-ray. So that is an optical specific property. And if you look at a spectrum, so this is flux versus X-ray energy, they're extremely soft. They're just thermal black body, million Kelvin gas with an area of roughly the event horizon of a black hole of 1 million solar masses. So this is the inner regions of a disk, basically. The X-ray is just hot gas at the inner edges of an accretion flow of a ball. Just, you also can't fit this with T to the minus 5/3. Okay, so, we have loads of data with some of these TDs. We have beautiful data sets. We have multi-wavelength, multiple optical UV bands, really long baselines. So how can we use this going forward is the question. And this is going to become an increasingly important question because our observational discovery rate is increasing rapidly. So the first few TDs were discovered by Assassin. They found about 1 a year. I am obliged to say that people found TDAs before Assassin, otherwise I get in trouble, but there was a handful from X-ray surveys, Rosat in the 90s. ZTF then came along in 2018, moved this from 1 a year to 1 a month. Together, this gives you roughly 150. And Rubin LSST is supposed to find 1 an hour for a decade. So if you don't know how many hours are in a decade, that turns out to be about 80,000. Okay. Whether we will classify all of these as TDEs is a different question. We have a good constraint on the rate and we know the sensitivity. So 1 an hour will be in LSST is the accurate statement. Whether we can classify them all is the hard. Okay, so this is going to be a huge resource if we can turn TDEs into a probe of black holes. So this is why you're going to hear more and more about it. Okay, so we have about 150, so we can develop theories, we can test them on this smaller population. We're going to have a huge influx of data, so ideally we'll solve this problem before LSST comes online. They could be very powerful probes if we can get this right. And an unfortunate, possibly hard observational requirement is that you really want to be able to relate optical data to physical parameters. If you have a really good theory of radio emission, you're going to be limited to tens of TDEs of the next decade, because that's really expensive data to get, whereas optical data is cheap. Okay, so what have we been working on? We've been working on relativistic accretion models of arbitrary events. So yes.
So we have, for example, like Chime does do very large all sky radio surveys, and they found a bajillion past radio bursts. Should they find any TDEs? Is SKA going to find a ton? Or why would they not have found them?
Great question. They're quite faint. Their luminosity is about 10 to the 38 per second. So I don't know. The radio people I talk to, it's all follow-up sensitive observations.
Is SKA going to be able to do anything?
Don't know the answer to that question. Sorry. So I want to boil this TDE down to the simplest theoretical problem that maintains some of the information, which is the following problem. I put a black hole in the middle. Let's say it's 1 million solar masses. And I put half a solar mass in a ring at the tidal radius of a 1 solar mass star. Okay, so I'm just going to ask the question, how does this ring evolve? This is my 0 for the model of a TDE. And then the question becomes, how much of this multi-wavelength data can I describe just by an evolving torus of material effect? Now, we don't expect it to explain everything. I mean, if it does, that'd be fantastic. But the information it can describe might be useful, and what it can't describe tells us about additional physics we need. So this is the problem we set up. So just do some pen and paper fluid dynamics in GR. What this means really is you, of course, just conserve mass, angular momentum, and energy. So, I have some disk that I'm going to assume is thin, in that the height of the disk is small compared to the radius from the black hole. I have some box of gas in my disk, and I conserve mass with a density rho and a fluid velocity u. Okay, and in full GR, this looks exactly the same as a Newtonian. I also conserve angular momentum, so of course fluid is not just flowing radially, it's orbiting the black hole. It has the angular momentum budget of the star that came in. I'm going to bunk all of the complicated GR MHD physics that people love simulating into one effective stress tensor component WR. So this is correlated magnetic fields, Reynolds stress. You can think of it as a viscosity if you want, but this is the IAS, so we should be better than that. It's a component of a stress tensor. And then you write all the ways down. This again is in full GR, which you can move angular momentum around. So this is just mass conservation again. If you deleted mass from the system, you'd remove angular momentum. If you flow down an angular momentum gradient, then your angular momentum of your gas changes. This is a torque from my stress. And in relativity, photons carry angular momentum. So if I radiate emission, and these are very bright systems, they will carry angular momentum away, which will change the dynamics. And then I'm going to assume that all of the energy I dissipate locally will ultimately leave the system as photons. Just energy balance, which lets me relate the temperature to the density and the stress and the flow. And if you bring this all together, you get the relativistic analog of the classic Lynden-Bell-Pringle equation. So it's a 1D partial differential equation, which relates the density and the stress and various properties. Okay, once I solve this equation, I can get the temperature of my gas as a function of radius and time. And this is a relatively trivial problem to solve because you can rewrite it as a pure diffusion equation by making various variable transformations. Basically, what this tells you is that to leading order, accretion in general relativity is the diffusion of some variable chi, which has dimensions of energy, with in angular momentum space. So H has dimensions of with some nonlinear, in general, complicated diffusion coefficient, but this is ultimately all accretion is. So it's a diffusion equation of energy and angle.
So rho here is sigma?
Yes, it's sigma. It's a vertigrated interface.
Leading order in what?
I've assumed that it's thin, so it's cold. I've assumed that the radial velocity is small compared to the angular velocity. And I've assumed that this WR phi is in some sense well defined, so that there is a local stress. So angular momentum transport is a local process, basically. So in that, which you can make precise, of course, in that limiting procedure. Okay, so you might want to, this is not the order in which we did all this science, but you can test this against full GRMHD, right? So people here and in Princeton run these massive GRMHD simulations of tori. Okay, so you put a bunch of gas down, there are magnetic fields, it goes turbulently unstable, and it evolves for 1 million, 10 million GM over C cubed. Okay, so what I'm plotting here is rho times R cubed. So this is basically d mass of disk by d log R. You can see that this is not even remotely thin. It launches winds. In fact, I think the magnetic field in the inner regions went mad. Okay, so this is all the things that thin disk theory is not supposed to be able to reproduce. But you can have a go anyway. So up here, I take the bound mass in GRMHD. I take d mass of disk by d log R at various times, which I show by color. And then I just take a pen and paper the nonlinear diffusion equation, and I compute at the same time the evolution of the bound mass. And you can see that a pretty good approximation, this pen and paper solution is reproducing the bulk motion of much, much more complicated theories, geometry. So this makes you feel confident that you're not completely wasting your time developing this theory for observation.
With one caveat, right? You didn't know what W was.
Didn't know what W was when we were fitting the observations. You can fit it to this profile. It's an effective fudge. We find that a WFI that grows with radius best describes the evolution, which is not what I used to fit observations. That's because this is 2025 and all the observations were 2021.
What was the profound radius?
R to the 0.3, so a week growth, and that's not a proper fit. That's just by eye. And as well as getting the sort of bulk flow of the material, if you ask what is the accretion rate onto the black hole, it's completely wrong for the first 1,000 GM over C cubed, which for a TDE is about 2 days. And then it does a pretty good at the decay of m dot onto the black hole with time. So yeah, this is probably going to probe an observation.
Why aren't your approximations getting worse over time?
So GR thin disk has no mechanism to wait for the MRI to kick in. So its early time evolution is poor. It's a diffusion equation. So when there are large density gradients, it evolves quickly. So at early times, it wants to evolve rapidly, and that actually puts it in a regime when it's not that, because it's assumed a small diffusive evolution. So it's not actually a particularly self-consistent theory early on. And so you have to put more mass into the analytic theory to compensate for this quick accretion at early time. Okay, right. Okay, so back to thickness observations. You have a diffusion equation that you're happy is at least capturing the gross evolution of much more complicated theories. You can then, once you solve for the density, you can get a temperature out at each radius and time, and TD disks are very optically thick. You've dumped a star on small scales around a black hole, so the emission that comes out is going to be well approximated as thermal at each radius. So what you're going to end up with something that looks like this. You have a series of annuli in your disk, each with a different temperature and area. Okay, and then my flow will evolve dynamically, the temperature will change, the size of my disk will change, and I'll get a sequence of local thermal spectra, which will give me some integrated SED that I see in my telescope, and this will vary with time. Okay, so here is, let's do this a little bit more, not as a cartoon. Here is my initial ring, okay, that I put at the tidal radius of a 10⁶ black hole, which is over here, and it's got 0.2 solar mass in the disk. Anything that crosses the black line is lost into the black hole, and the evolution looks like this. So of course it doesn't stay as a ring for very long. The diffusion equation doesn't like rings. Material rushes in, okay, that's this turbulence, diffusing stuff around. The temperature goes up. This is physically easy to understand. I'm getting deeper and deeper in the potential well of the black hole. There's more free energy to liberate. I get hotter. Then my temperature drops with time. That's just because I'm always losing material into the black hole. My density goes down, and so does my temperature. Some material runs away from the black hole. Okay, that's to conserve angular momentum. If I take a ring and just put it all on the black hole, I've lost all my angular momentum. Angular momentum is conserved, so some material must flow out to soak up this angular momentum of the inflowing.
The moments of time, just generations.
What's that, sorry?
Repeating the moments of time.
These are just in days. This is actually a fit to some data which will come. So what would you see at Earth? So put this 90 megaparsecs away, because assassin 14 Li is 90 megaparsec away. This is going to be the disk again at the bottom. This is what you would see with the Swift X-ray telescope. This is what you would see with HST. So as my material rushes in and I get hotter, my disk SED moves to higher energies. It's a thermal spectrum. I push some into the Swift X-ray band. My X-ray luminosity goes up. As I lose material into the black hole, I get colder, my spectral peak drifts to lower frequencies, I get less X-ray flux, my X-ray luminosity goes down. So the vanilla zero order prediction of this theory for X-ray light curves is they go up and then they come down. Something very different happens over in optical UV. So the flux goes up for 100 days, but then it just sits there. So it sits there for 1,000 days in this simulation. It will sit there for, in principle, decades, as long as the disk stays in this thermal dominated state. And the reason for this is you have two competing effects that cancel out. So I have a thermal spectrum and I'm cooling it down at all times. So a fixed area thermal spectrum that I cool down decreases the flux at all frequencies. I'm decreasing the temperature because I'm losing material. But my disk is always getting bigger because it has to conserve any momentum. And if I take a thermal spectrum and make it bigger, make the area bigger, I increase the flux at all frequencies. And it just so happens that if a typical TDE parameters in the optical and UV, these two effects cancel out. You end up with time independent to leading order like. And this really does seem to work on the zeroth order level, or maybe even first order. So this is the X-ray flux that Swift saw for Assassin 14 Li over 800 days. The blue line is this simulation I just showed. Now, of course, the real world is more complicated on short time scales than a diffusion equation, but just like the GRMHD, we seem to be capturing the bulk evolution of the light.
What was known about the system before the TDE? Like the black hole mass was known?
You know the galaxy mass, we have the velocity dispersion now, bulge mass.
So all of these events are in locations which are, some of the physics is known before the TDE.
Yes. So that's not quite true anymore because we're finding more in what we presume a satellite dwarf galaxy, where the TDE is bright enough to see in a survey, but the satellite dwarf was too faint. So it just appears out of nowhere from our perspective, but that's just because the dwarf is galaxies.
And also, if you want in the future to find the intermediate black holes
Exactly.
through TDEs.
Yeah, exactly.
So how would models, because there must be degeneracy, like this model assumed like 1 million solar mass black
So
hole.
so it turns out that that's not true when you have UV and X-ray. You break this degeneracy. So this ended up being 2 million, and you measured the star mass. Okay, so what happened? Yes, go.
So I was wondering how sensitive is the model to your initial condition? So change the radius or
So
the
it's a diffusion equation, so it cares about the initial scales. So it cares about the mass and the radius, but it quickly loses memory of that initial condition, but it retains memory of the radius. So in the full package that you fit to data, there are 3 parameters, and then post hoc, you check that they're reproducing on the population level, the TD physics you expect. So it does seem to be, if you throw this into a maximum likelihood thing, that the radii of the rings that come out scale with black hole mass like the tidal radius, which is interesting because, well, that's a nice
mean it's just the typical size of your initial condition rather than the radius.
Yeah, I mean, if we probed, you wouldn't expect to get the rise in the X-ray light curve, correct? For example, which is much more sensitive to the initial conditions. But, after 2 diffusion times, the diffusion equation doesn't care about much. And this is what it looks like in the optical UV. So this is very much not direct emission from an accretion flow, but we kind of knew that already. So something produces the shocking gray optical flare that you find in your optical survey. There are models for this optical flare. None of them are particularly successful. But if you wait 1 year, whatever's producing this optical emission continues to decay away. And what you're left with is an evolving accretion flow in the optical UV, which becomes brighter than whatever was. I don't really want to get into details of what this is. It's controversial and there's lots of very unhappy people in the field, but all I'm going to say is that if you are patient and wait, we have a model that explains the late time optical.
The calculation of the spectra is done just assuming, going by the radiation from.
So it's a local color corrected black body, and then I ray trace the photons.
The scattering opacity items.
Or a calibrated model of those scattering effects that people around local atmospheric codes, and as a function of the density and temperature.
Expert library or
This is now in expec. This was originally me coding it up during my PhD, but it's now, yeah. And we follow the photons, so we do ray tracing, light bending, and Doppler and gravitational redshift as well.
That's probably most important for X-rays.
For X-rays, for optical, this is Newtonian stuff, yeah. For the X-rays, it does make a difference. So just to advertise some work from Muriel, you can go beyond, who's a grad student at Johns Hopkins. You can go beyond light curve fitting and you can do full SCD. So rather than taking an integrated X-ray luminosity, you can actually fit, this is observer frame, so there's absorption from gas and dust. This is rest frame. You can fit the full SCD, evolving with time from optical UV all the way through X-ray. And it works beautifully. This is in XSpec. Many different TDEs. This is an intermediate mass black hole, for those of you who are interested in those things. This is a very slowly evolving TDE. It took about a decade to change in X-ray luminosity by a factor of a few. You can even just do this with an X-ray binary. There's nothing special about TDEs. You know, X-ray binaries sometimes do soft flares where it's just an evolving disk. The same theory works pretty well for X-ray binaries as well. So it's just time evolving black hole accretion.
So that's assuming that you have pre-existing disk.
Pre-existing disk and then some radius, you get a spike in the stress, which causes a
stress.
So it's rather than dumping mass, it's some spike.
It's like dwarf nova oscillation. Oh, sorry.
It's similar. So yeah, the physics is probably that the hydrogen ionization instability kicks in some. That causes your stress to rise, which because I can write as a pure diffusion equation for sigma times WR phi actually satisfies the same diffusion equation as just dumping more mass. Well, that's the hope. This is very much in prep. We just wondered if it would work for an X-ray binary, and it seems to do, so we're thinking about what that was. Okay, so now you want to go from a theory that is nice, but computationally very expensive. These are quite hard fits to do. It's a large parameter space, to a product for the community, effectively. So,
How large is the parameter space for?
So we have 7 3 parameters: black hole mass and spin, disk mass, radius, viscous timescale or diffusion provision, observer inclination, and how much hydrogen is along the line of sight. So we correct for the stuff we know is in the Milky Way, but we don't know the hydrogen density absorption through the host galaxy. So you have to fit for that.
Is this effective stress that you mentioned, you just calibrated to a DRMHD simulation and leave it fixed?
I assumed WR phi equals W equals constant to make my life easy for solving the diffusion equation, which is not that far off R to the 0.3. The hope is in the future you can calibrate it to GRMH. Constant W is in some sense natural because the viscous time is directly proportional to the orbital time. At a given radius. So, which is not obvious, but that turns out to be true.
How non-linear is your diffusion equation?
So
coefficient.
It's linear in this limit. If for an alpha model, if you want to do an alpha, it would be nonlinear. It's still a mess because there's all these GR corrections, but it's a linear diffusion equation. We actually have analytic Green's function solutions for it.
Obviously, there's many complications, but one is that they're supposed to be super Eddington for a while.
Yeah, so
Maybe the most important assumption that might affect would be the assumption that the dissipation is local and that all the energy radiated with any given annulus is radiated there. In super Eddington, you wouldn't expect that to be true.
indeed. So, I mean, our approach at the moment has been to fit the data and then post hoc check the volumetric luminosity. And as a general rule, we find they hit 1 Eddington at early times, which probably tells you that M dot is indeed super. So yes, at early times, this is of course the model is being pushed into a regime that's not strictly valid. But yeah, as I will go on to say,
With super Eddington disks and
so you could, but you want to do this time dependently. So you could, people like to fit sequences of steady states, which I find mathematically offensive. okay? Because the steady state doesn't change with time, so you can't just change your integration constants with time. Then it's no longer a solution. So if a slim time-dependent relativistic theory were developed, that would be better.
Or I mean, as we've discussed, we can just get how to run.
Yeah.
Run disk for 10 to 7 amp.
Yeah, I think taking this and comparing to GRMHD is definitely where we need to. Okay, this is great. You can't do this for LSST is the point, okay? It takes more hours to fit the data and get a mass than your discovery rate in hours, if you see what I mean. So this takes a couple of days per source to get a posterior on the black hole mass. So you want a product that you can apply and get a mass with more uncertainty, but much more quickly. So that is what we did in 2024. So I want you to think like an optical astronomer. This plateau is really convenient for you as an observer because it is described, it has one observational degree of freedom, which is the height of the flat line effect. Okay, if you write a HST proposal here at day 300 and it's rejected, and you write it again here at day 800, you will find the same answer. Okay, no matter when you observe this system, you always get the same answer, so you have one observational degree of freedom. The claim is that the system is in a relatively nice state at this point. We claim to understand the physics of why it's a flat line. So if you could relate your one observational degree of freedom to the system parameters, then you'd have a powerful probe of supermassive black hole demographics.
How long is this plateau state expected to last for?
That's a fantastic question. So as far as we can tell, it's longer than 2014 to now, which is the first Assassin TDE. We have a Hubble Space Telescope proposal that's going to the Rosat ones from the 90s. So that would push this to 35 years if they're still there. In theory, it could be centuries, but we would expect some sort of low hard state transition that we see in X-ray binaries to happen at some point. But observationally, at least 10 years, maybe 35. We're going to check that this cycle.
Isn't fitting a 7-dimensional parameter space to one data point difficult?
Yeah. Well, I'll explain what we're doing now. Okay.
Is the plateau always in the optical, regardless of the mass of the black hole, even for?
So you need to make the mass of the black hole so high that the disk SED peaks in the optical for it not to be a plateau. But the mass of the black hole that high swallows stars whole rather than disrupt them. So for pretty much the whole parameter space, it is flat, at least over 5 10. Okay, so with pen and paper, you can solve the question of how does my flat line depend on system parameters, because you have as many unknowns as you have constraints. So the first is that your temperature always decreases with time because you're always losing material into the black hole. If you massage the diffusion equation, you can learn that it drops as a weak power law with time. You conserve angular momentum, so your disk always gets bigger. Again, massaging the diffusion equation, you learn that's also a weak power law growth with time. You have a constraint on the integrated energy that can come out of this disk over all time because you had one star at the start and you have about 10% efficiency. So integrated over infinite time, you cannot violate this constraint. Black hole disks are dominated by their inner regions, so the emission from black hole disks is dominated by their inner regions because they're hottest. And you know the rough radial scale you started with because you had to rip apart a star. Now, you can combine these 5 constraints to get, depending on which bit of the spectrum you're in, provided it's not the Wien tail, the scaling of nu L nu, which I see at 1,000 days with system parameters. We get lucky, which is that no matter what bit of the spectrum I'm in, I get a black hole mass to the 2/3 power. And then, of course, there is scatter from the different stars that come in, the different inclinations I see, the different viscous times. But this is effectively time domain astronomy n sigma. There's something I can measure which gets me a black hole mass with scatter. Now, you want to understand this scatter for the exact point you raised, which is I have a large parameter space and I'm trying to just relate it to one number. So you do that by just sampling 1 million TDE systems. Theoretically, You do this for a uniform grid in black hole mass. For each black hole, I throw stars at them. I ask, could they be disrupted? If so, where would the disk form? I then solve that. I evolve that for 1,000 days. I sample stars in a sensible way. I randomly orient these disks in the sky. And I do a uniform distribution of black hole spins for want of a better idea.
What kind of simulations are these?
And this is the diffusion equation. This is the one.
Diffusion equation needed the radius of the ring. So you say.
So I solve the GR tidal force problem to work out if it could be disrupted. If it could, I work out where it would circularize. I then solve the diffusion equation. So I trialed more than 1 million systems and a bunch of them failed to be disrupted. You just keep the million that were disrupted.
So what are you assuming for the circularization radius?
I just conserve specific angular momentum of the incoming star, given the mass loss. It's a specific angular momentum. And this is what you find. So this is then nu L nu at 1,000 days versus black hole mass. And the color is the log of the number of points in each pixel. So the black dashed line is your pen and paper. The 0 to 100 scatter is huge because it's a 7-dimensional parameter space and they can all in principle vary by a large degree. But this is the log of the number of points. So at 10 to the 6, there is one very, very faint one very, very bright one. But the vast majority, thousands and thousands of systems, lie in a relatively tight band. So you can pose the question, if I see a given nu L nu and I project across this massive distribution, what is the black hole mass I would infer? And it turns out to be about half a deck scatter at one standard deviation.
That's assuming you see everything. About the selection that you preferentially see very bright things.
So yeah, sorry, this is given a measurement of L. So this is not talking about distributions. This is talking about one thing I know of. Okay, so that's what you want to do. You say, I'm running out of time. You say you can relate L to mass of half a deca scatter. So then you go away, and this was done in 2024 when there were 84 optical TVs. What you do is you take the light curve, you fit some phenomenological decay to the early time, plus P for plateau, right? And you constrain P from the data, then you're going to get independent estimates of the black hole masses, and you're going to compare to this relation. So of the 84, there were 50 that we could constrain P robustly. A bunch of them had gone off in the last year. So you're never going to find the late time emission from early time data. Some of them, the galaxies are too bright. They're brighter than the plateau. Some of them are too far away. It's too faint to get. We have 50. You go away, you get velocity dispersion measurements, and you plot them over your simulation. So the colored points are real TDEs where you get either n sigma, or if you can't get n sigma, the galaxy mass, use a scaling relationship, and you plot the nu L nu you've measured. And you get, okay, so clearly the data seems to know about this is absolutely not the way around you want to do this problem. You do not want to use galactic scaling relationships to test disk theory. What you want to do is you want to take these nu L nus you've measured, turn them into black hole masses, and then see what happens to galactic scaling relationships. So this is then black hole mass versus galaxy mass. The gray points are Jenny Green's compilation. The blue points are TDs. So you can see it's entirely consistent with the known galactic scaling relationship, just extrapolated down all the way to 10 to the 5. We fill in a different region of parameter space because tidal forces are larger and lower black.
Wasn't there on Tuesday there was a talk in the Bacor lunch with a similar plot, just different technique, and all the lower mass were higher.
If you believe in galactic scaling relationships, every other technique fails because they find no correlation between black hole mass and galaxy mass, black hole mass and velocity dispersion.
So she claims she has observations in the low mass regime.
Yeah,
Specifically dwarf galaxies. I mean, how many dwarf galaxies range?
I think none. This is ZTF. These are
outside of the plot.
These are just low mass normal galaxies.
Okay, so I have 5 points with outside of this plot.
Well, that's
what you're saying.
I'm thinking it was specifically dwarf galaxies, so they're target.
Same is true for M sigma, so you can fill in the lower end of the velocity dispersion relationship as well. And then since our paper, Paige Ramsden, who's a grad student at Birmingham, has added them to bulge mass of a galaxy versus black hole mass, and they're the green. So
And
you see-
sigma doesn't seem to fit.
Okay, so there's a bias here because it's easier to detect brighter things. So at fixed sigma, you find higher mass black holes with this method. So really, I'm plotting brightness on the y-axis. So it's easier to find high mass plateaus. So for a given sigma, I will populate these ones seem to be being filled in with more and more data. You just have to stack your observations for longer and longer. But that will be an interesting question when we have many, many more. I guess in the sense that M correlates with sigma, this is successful, which it doesn't with other TDE techniques. They are consistent if you have a Malmquist bias and a fluxiometer, so I promise you. Okay, okay. Yes. The next question you want to ask is, rather than having one TDE and getting one mass, I have a distribution of luminosities of my TDEs. What is the distribution of masses? So then you just take, so this is my distribution of luminosities. These are PDFs. I have 60 UV plateaus, 44 X-ray peaks, 90 optical peaks. Okay, this is already out of date. There's way more TDEs now. These are the PDFs, so this is just the count at Earth. This is the intrinsic rate. And the question is, can I parameterize a black hole mass function that reproduces these distributions given known TDEs? So the point basically being, and I'm going to go through this relatively quickly, the observed distribution of black hole masses is clearly not uniformly distributed, while my simulation was uniformly. So I can write down a broken power law, say, for my black hole mass function. I can then repeat the 1 million TDE sampling. This will give me a predicted luminosity from a predicted distribution of plateau luminosities, which I can compare with the observed distribution. And that will give me some likelihood of seeing this distribution of plateau luminosities given two power law indices in a break. Okay, if I can define a likelihood in terms of parameters, I can maximize that likelihood. You can reproduce the PDF of the plateau luminosities in this technique. I will discuss the black hole mass function in a few slides. You can just reproduce the PDF, the CDF, the 2D profiles for plateau luminosity versus black hole mass. Just to convince you that we're not, a critique could be, well done, Andy, you've discovered statistics. Okay, you had some data, you fit a model to it, and now you're telling me that the model reproduces the data. That's entirely different. To convince you that we're doing something sensible, I will show you that you get the X-ray distribution for free. So you fit to the late time UV distribution, which is this blue distribution, and then you get this X-ray peak distribution for free. Okay, this is because the disks I see at late time in the UV are producing my early time X-ray, if you remember the light curve. So you take your best fit mass function for the UV, you sample 1 million TDEs, and rather than ask what was the late time UV, you just ask what was the peak of the X-ray light curve, and then you get this distribution, and then this is the data you get from a whole range of surveys. And it's actually, if you look at the CDF, they are consistent with being drawn from this model. So this really does seem to be the mass function of TD. So the question you want to know is how many intermediate mass black holes are there? You've constrained the mass function. So there are two mass functions here. The green is what we observe. Okay, so we observe a flat distribution in black hole masses and TDEs. There's then a very sharp suppression above 10 to the 8. This is because 10 to the 8 is the black hole mass where the event horizon is equal to the tidal radius for a solar type star. So you just swallow stars whole above here.
there's some scatter with the spin regarding.
Yes, if you had enough TDEs, you could try and constrain the spin distribution using when this turns. I've checked, there's not enough data at the moment. There is a strong observational requirement for the observed mass function of TDE black holes to turn over just below 10 to the 6. Do you think that's fantastic? Intermediate mass black holes are rare. Maybe they're all black holes are born in the early universe at 10 to the 5. If you correct for the fact that a smaller mass black hole has a lower Eddington luminosity and so it's harder to find, you get this blue distribution. And so either the black hole mass function is sharply turned off at 10 to the 6, or it keeps on going and there are loads and loads of intermediate mass black holes. And the reason for that is if you ask, given the Eddington luminosity and my flux sensitivity of ZTF, how many intermediate mass black holes should they have found? The answer is a half. Okay, and I think we've seen 0. So of course that's not constrained. So to quote my job applications from last year, LSST will constrain this over the next decade, hopefully. I think this is a very exciting concept. Okay, I'll finish there. Thank you very much for listening. Great question.
No, I'm sure this is a sensible question, but you show this works for X-ray binaries. Yeah. Then for these black holes, you're trying to measure the mass. Yeah. The X-ray binaries, you know the mass in many cases. Can you use that as a?
We've done it for one X-ray binary and we get 10 solar mass. So.
No, the X-ray binaries, which you know the mass pretty.
The dynamical mass is 8 plus or minus 2. So they are consistent. I don't want to claim that this works based on one.
Sure, but is it easy to do it for all of them or?
Yes, we asked an X-ray telescope for some money to do that. Hopefully they will give it to us.
So this accretion theory, machinery that you developed in the beginning, I mean, in the Newtonian case, it was known for more than 4 decades. I mean, the calculations like you showed, flat UV thing, this is, Kaniza, Goodman, 1990, and so on. So what's different? Is it just the GR effect? And if you were to compare your GR calculations with the Newtonian calculations, what would change?
So in the optical UV, if Knizia, Goodman, and Lee had pushed this further, they could have found this scaling relationship up until about 10 to the 7, 10 to 7 a bit. Then the bit that produces optical would start to become relativistic and it would change a little. But the flat line could have been pushed by Knizia, Lee, and Goodman, and it will be in that.
They have the figure.
They have the figure, but they didn't do the scaling across the population. The X-rays you can't do well in the Newtonian theory because you really are just.
So really the corrections come in.
Doing a Newtonian theory for the X-rays is not a good idea because you really are just seeing and the full SED therefore, which is our best mass measurements, that requires the relativistic theory because you're coupling the X-rays and the in one thing. So yeah, if you just wanted the optical, I mean, we were interested in the X-ray and then we discovered.
So even like assuming, not the Shakur-Sinaev, but like
Lindenbaum, Pringle,
or something like that, will not do that.
So what you really want to reduce, what you don't want to do is have all these m dot 3 parameters. Each epoch has its own m dot. No matter how many epochs of data we have 7 parameters. It's the initial condition, the black hole, and then we solve an evolution. So for the X-ray binary I showed, there's 80 epochs of data. So the standard approach, that's 163 parameters. Basically have a size and a temperature each time. But we can reproduce this data with 7. An initial condition and an evolution equation. So I think that's a more. It's just a better.
Sounds like you're making some approximations to make the diffusion equation solvable.
Yeah.
You can also just solve diffusion equations.
Yeah, exactly. So I just wanted to simulate a million. And it was, if I have an analytic solution, I can do that. I didn't have the computing.
Like that would be the bottleneck. For a
So
simple
it's a relatively, it has a singularity as a diffusion equation at the ISCO, which is a little bit tricky to handle. I didn't have the computing might of the IAS at the time. I had my laptop in Oxford, so I used a linear diffusion technique. And the GRMHD is better described by a linear diffusion equation with some tuned index than the non-linear ones, because the stress doesn't appear to care about the density. It's entirely magnetic driven stress.
About the M sigma relation.
Yes.
Maybe it's pushing the delta with error by so much, but can you, from your results, can you claim that you see flattening? Same sigma?
You could claim, but it's, I don't know, I think it's Malmquist bias. So remember there is 100 TDs of which we can measure the plateau for about 60. So we're missing 1/3, and they are the faint ones, which are the low mass ones. So we are working to try and quantify this precisely. The fix to these points is shallower.
But they can have dynamical arguments that it should be shallow.
Yeah, so that's why I'm
number
nervous about claiming it, because I know it's an interesting question. You want to be really careful that it's actually shallower and you're not just missing the low mass ones.
You mentioned the early optical light curve was controversial. Could you say something more about that and whether it's ever going to be possible to figure out something about circularization?
It's actually, purely empirically, they're very simple. So if you take the masses you measure from the late time and just plot the early peak, it scales linearly, which tells you the Eddington's probably at 4. And the energy also goes up with mass. So the reason it's controversial is that every model published has the opposite dependence. So the index on the power law scalings has the wrong sign. So everyone thought it just traces the fallback rate, which goes down with black hole mass, so they should all get fainter. But the data at many sigma confidence goes up. So it's controversial in that everyone has spent a lot of time pushing models that just don't reproduce the data.
Is that time period related to the circularization, or is it?
So if you ask the question, what is the energy I need to shed to go from a star on a parabolic orbit to a disk on a circular orbit, that pretty much reproduces the energy you see in these flares. So my assumption is, working hypothesis is that it is the energy you need to shed to form a disk comes out in these optical flares at the edit. So if that's,
maybe we can learn something about circularization.
yeah. I mean, there's mountains of data. The correlation is really tight. It doesn't even look like you need much beyond just the mass. And you know the peak luminosity and the energy, so you know the time scale and so on.
Just a quick follow-up question. If that is true, this is due to the circularization, then the circularization is gonna be taking about a year, right? This is where the optical flare merges this is plateau. But then your initial condition is that you already have all the mass sitting in this narrow ring. And there is no mass.
So this is why it's more complicated, because we know that there are X-ray flares which require a lot of mass, about 10% of the solar mass, coincident with the optical peak. So the energetics of this circularization seems to give you the max scale, but the time scale is completely, because you get X-ray, which you can only get from a massive accretion flow at the same time as the peak of the optical. If you can work out this flare, please tell us, because we're going around in circles as a community on this. So it's a hard observational requirement that you need accretion of 10%, 20% of the solar mass at the time of peak optical light in some TDs. It's a hard.
This unexplained peak.
This unexplained peak. Okay. It's a hard requirement that you need optical flare luminosity that goes linearly with black hole mass and an energy that grows with black hole mass as well. Those are, and sometimes the X-rays switch on at 500 days after peak. So there's also, some of them are bright X-rays at the start, some of them are bright a year. I'm happy to go on empirical routes. It's an optical flare. It's very helpful for finding these things, and we do the science with.
Well, let's continue this discussion over lunch and